Hi everyone, welcome back to 2.4, where we really start talking about like the big study to college algebra, and that's functions. So like I said, at the end of 2.3, functions are going to carry us through most of the rest of the way. So yeah, we're gonna get right into that here. So functions in general are rules that assign elements from one set to exactly elements in another set. So technically you can have a mapping where any number of x's go to any numbers of y, and you can have whatever you want. But for functions, we very specifically want rules or mappings where elements in some starting set x get mapped to exactly one element in some ending set y. Well, this starting set x we would refer to as the domain, and y, this ending set, we would refer to as the range. Domain is where we start, range is where we end. And maybe you're already starting to think about x's and y's. What do we usually plug in? Do we normally start with x's and find y, or do we normally start with y's and find x's? It's almost like I use the right letters when I'm defining these sets. So the rules for functions, again, is that every element in set x, every element in the beginning set x, has to be assigned to something in y. However, not everything in y has to be used. Everything in x has to be used, not everything in y. Likewise, every element in x can only go to one element in y. However, multiple x's can go to one y. It's just that x can only be used once. Y's can be used more than once, but x's may only be used once. So correspondence diagrams, we're not going to spend a whole lot of time with this, but I'm going to move to the whiteboard just to show you some examples of what would be a function and what would not be a function. Okay, so now we're on the whiteboard. Just in general, what a correspondence diagram would be is something like this, x and y. Let's say we have 1, 2, 3, 4, 5, 6, and just any mapping, just to show you what a general mapping could look like. 1 could go to 4, and 2 can go, and 2 can go to 5, and 1 can go to 5, and 3 can go to 4, and 3 can go to 6, and why not? 3 can also go to 5. Just this mapping of x's to y's. Now, I'm not going to comment on this one. This is not a function by any stretch of the imagination, but let's go into some of the properties specifically of functions. I just wanted to show you a very quick correspondence diagram. So let's say we have some set x, some set y, and we're mapping from x to y. Okay, so let's again go 1, 2, 3, 4, 5, 6, 7, 8. So the rules of functions are as follows. First rule is that every x must be used, and 2, every x can only be used once. Okay, so for example, 1 can go to 8, 2 can go to 6, 3 can go to 5, and 4 can go to 7. This checks both rules. Every x was assigned to something in y, and every x was assigned only once. So that's okay. There's nothing wrong with that. Now, another example of something that would be okay would be something like 1 goes to 5, and 2 goes to 5, and 3 goes to 5, and 4 goes to 5. Just to review the rules again, well, every x was used, and every x was used once. We don't have any rules that run against multiple y's, or y's being used multiple times. So as long as it checks these two rules, we are totally okay. All right, let's do an example of something that would not work. So for example, let's say 2 goes to 6, 3 goes to 8, and 4 goes to 7. Okay, let's go through our two rules. Every x must be used. Well, 1 wasn't used. Well, that's kind of a problem. That fails the first rule. So this, as written, is not a function because x equals 1 was never used. Okay, so that would be an example of something that isn't a function. Well, let's do another example of something that is not a function, but maybe it violates the other rule. Okay, so let's say 1 goes to 5, and 2 goes to 6, and 3 goes to 7, but 3 also wants to go to 5, and 4 goes to 8. Well, let's look. Was every x used? Yeah, 1, 2, 3, 4, 5. 1, 2, 3, 4 were all used. However, not every x was only used once. Look at 3. 3 went to 2 things. It went to 5 and it went to 7. That violates the second rule because every x was used, sorry, at least one x was used more than once. So even if one x does this bad thing, that's all that matters to make it fail. So that's how we like visually define functions. Of course, we're going to do this more with algebraic methods and terms, but I still wanted to show you this nonetheless. So I'll see you back at the presentation. And now we're back at that presentation. Okay, so let's now introduce function notation. And what we use is this f of x in parentheses. This is not f times x, right? In the past, we have used parentheses to denote multiplication. This is not that. This is f of x. Or in another way, saying the value of f, the value of your function at some x value. Okay, well, we also use y to denote the exact same thing, right? We can say that y is the value at x. So in a lot of ways, y and f of x are interchangeable. And maybe at some point in this section, we will do something where we literally interchange f of x and y. So like I said, f of x is saying value of the function at x. Y is also saying the value of your equation at x. So they're very, very similar. If you can write something as f of x equals or y equals something specific, where you get only one y value for every x, right? Correspondence diagrams. If we had something where every x only goes to one y, we are good to go, okay? They would then be a function. So let's do that algebraically. What we want to do is get exactly like I have written here, y equals one specific thing. So if we can write this as y equals where every x only goes to one y, we are good to go. Okay, so we're going to solve for y, right? That's what y equals would be. So let's subtract 6x squared on both sides, and let's divide everything by -3. Now, this, let's see, does every x go to 1y? When I plug in x, how many y's do I get back? Well, if I plug in x equals 0, totally arbitrary, let's plug in x equals 0. Well, 0 squared is 0. 2 times 0 is 0. 0 minus 4 is -4. But that doesn't really mean anything. What we're most concerned about is that when we plugged in 1x, we only got 1y back. That's the key here. So every x only goes to 1y. No matter what we plug in for x, we can only get 1y back. So this is a function. Now you're probably wondering, how could this possibly fail? Well, let's do one like this. Let's solve for y. Let's add x to the fourth to both sides. Let's take the square root of both sides. But don't forget that when you take the square root of both sides, you get plus and minus. Okay, maybe we already start to see the problem. All right, let's plug in anything for x and see how many y's we get back. Let's again plug in x equals 0, because why not? Well, 0 to the fourth is just 0. 0 plus 4 is 4. Square root of 4 is 2, but then we tack on plus and minus to that 2. So when we plugged in one single x equals 0, we got two answers back. We got +2 and we got -2. One x went to two y's. So this is not a function. Okay. X plus y cubed equals 12. Let's subtract x on both sides, and let's take the cube root this time of both sides. But think back to 1.5. In 1.5, when we take a cube root or an odd root of both sides, we do not get plus and minus. So we can take the cube root, it's not an even root, and we are good to go. Well, you already see we don't have plus and minus this time. So let's plug in x equals 0. Why not? Well, -0 is 0. 0 plus 12 is 12. cube root of 12, no idea what it is, but point is we only got one answer back. So 1x goes to 1y. This is a function. All right, just moving up the ladder, let's say y to the fourth. You probably already know what's going to happen, but let's subtract x to the eighth, 15x to the eighth on both sides. Let's divide everything by -1. And now let's take the fourth root of both sides. But don't forget, when you take the fourth root of both sides, you again get plus and minus. Okay? And now you see, no matter what we plug in, we're going to get two y values back because of the plus and minus. So, not a function. All right. Another thing we're very interested in when it comes to things that are actually functions, not guessing and checking whether or not something is a function. Okay, we're given something, we know it's a function, we want to evaluate at specific x values. Well, to evaluate a function, simply plug in whatever value you want for x. So let's say f of x equals x squared minus 6x plus 8. Well, we moved from y equals x squared minus 6x plus 8 to just f of x equals x squared minus 6x plus 8. Let's say I want f of 3. F of x equals 3. Well, here, f of x, f of 3, the only thing that changes is wherever we see x, we're going to write 3. So plug in 3 in parentheses, and now it is just simplifying. 3 squared is 9. 6 times 3 is 18. 9 minus 18 is -9. -9 plus 8 is -1. The value at 3 is -1. That's basically the point. 3 comma -1. No different from how we have done it in the past. F of -2 says wherever we see x, plug in -2. Again, use parentheses. Be very careful. We've talked about this problem so many times. -2 squared is +4. -6 times -2 is +12. So we get 24. Okay. F of 1/2. Yeah, I know how much you guys love working with fractions, but same thing. All it says is wherever we see x, plug in 1/2. 1/2 squared is 1/4. 6 times 1/2 is 3. And I'm going to trust that you guys can add and subtract fractions. Okay, so you see the pattern here. Wherever we see x, just plug in that value. That's it. Nothing else. What if we want f of potato? Nothing says we can't do that. Well, f of potato says potato squared minus 6 times potato plus 8. Whatever we want to plug in for x, all it says is replace x with that value. Of course, potato is a little silly. I totally get it. But the idea here is it does not matter what is in here. All it says is to plug in that thing for x. So kind of moving in that same direction, what if we don't want to plug in just a single value? We want to plug in another expression. And we're going to do that quite a bit here and in the future. So f of a plus 2 just says wherever we see x, write a plus 2. So a plus 2 squared minus 6 times a plus 2 plus 8. That's it. This is foiling. This is distribution. And now just combine like terms. It doesn't always have to be something we can combine. It's okay. Alrighty, 4a minus 6a is -2a. 4 minus 12 is -8. -8 plus 8 is 0. A squared minus 2a. It's not as comfortable. I get it. We want to plug in numbers and we get numbers back. But that doesn't always have to be the case. And you're going to see in the future how we would get something useful doing something like this. Okay, for example, we can also do f of x plus h. Now, let's be very, very, very clear about something. I understand there is an x here and there is an x here. These x's are not the same thing. This is saying some single x value in space. This is saying the expression x plus h. So same thing. I know it already has an x there, and we have an x in our original function. That doesn't matter. Wherever we see x, we're going to write x plus h. And again, this is going to be foiling. You are going to FOIL, you're going to distribute, and you get to something that can't even be combined, but that is totally fine. There's actually very good use for something like this. I don't remember what section it's in. It might be in 2.5, but I can tell you for sure, those of you that have to take calculus in the future, you will see f of x plus h again. So again, wherever you see x, just plug in that thing in parentheses. All right, let's do negative 2x squared plus 5x. F of 0, wherever we see x, plug in 0. 0 squared is 0. Negative 2 times 0 is 0. 5 times 0 is 0. All right, whole thing 0. That's very exciting. F of negative 1, wherever we see x, plug in negative 1. Negative 1 squared is positive 1. Negative 2 times positive 1 is just negative 2. 5 times negative 1 is negative 5. Negative 2 minus 5, negative 7. F of x plus h, wherever we see x, we're going to write x plus h. I get it. I know it is uncomfortable because there's already an x there and you just want to plop on a plus h. Can't do that. Imagine this was an a. If this was a plus h, well, you'd already be good. You'd have nothing to worry about. But it is an a plus h. It's x plus h, and it functions exactly the same way as if it was a plus h. All right, this is foiling. This is distribution. All righty, FOIL the insides, then distribute negative 2, and that's all you get. We have to leave it like that for right now, and that's okay. Okay, well, that's the basics of function. That's probably one of our longest basics we've had in a long time, but yeah, so it goes. All right, domain and range. Well, domain and range, we talked about on that very beginning slide. Domain is the set of all places we start, and range is all the places that we end. So domain, in general, for algebraic functions, not like what we were doing before, is the set of all real numbers for which our algebraic function is defined. And we always write these things as intervals. Okay, another good way of thinking about it is the set of all x values that are included. Okay, what I mean by that is take the set of x values that when you plug it in, you get something normal back. You don't get like 2 over 0 or square root of negative 3. So by default, a function's domain is negative infinity to infinity, or all real numbers. However, we have some red flags that we need to bring up when they happen. First one is for rational functions. Rational functions are just functions with a denominator. And in that case, well, think about what causes problems when we're in a denominator. We can't divide by 0. So in rational functions, the denominator cannot be equal to 0. Okay. Square root functions. Well, we know we can't take a square root of a negative number, so we need to make sure the inside is not negative. If you have a square root in the denominator, well, kind of like a combination of the previous two examples. These two are kind of red flags on their own, these first two bullets. This third bullet, though, is a nice combination of them. Well, we just said square roots. The inside of a square root can't be negative. So that means it can be 0 and it can be positive, but if it's in the denominator, it also can't be equal to 0. So long story short, inside must be positive, not just negative, must be positive. So it can't be 0, it can't be negative, it has to be positive. If you have a rational and a square root, so for example, you have a square root in the numerator and there's still a denominator that causes problems, find the domains of each part and then take their intersection. This happens not frequently enough for us to, spend a whole lot of time doing it. So let's find some domains. Find the domain of 400x squared plus 236x plus 19,003. Well, look at the red flags that we have. We have rational functions, we have square root functions, and all even root functions, right? We can't take negatives inside an even root. But rationals, fractions, square roots, those are our red flags, and we don't have either of those here. How nice. There is no rational, there's no denominator, and there's no square root, so we have nothing to worry about. No denominator, no square root. By default, our domain is all real numbers, negative infinity to infinity. What this says is that you can plug in anything you want for x, and you will always get a defined number back. It might not always be a pretty number. It might be very big, or in this case, can anything be negative? I don't even think so. So, it might be very, very big and very, very ugly, but the point is it's defined. And that's the key to domain. Find the domain of 1 over 2x minus 6. Well, this is a rational function. It has a fraction. It has a denominator. And we want to make sure that the denominator never equals 0, right? The only place that this could be undefined is when the denominator is 0. Well, rational denominator cannot equal 0, so we set the denominator not equal to 0. You can similarly set it equal to 0 and take those values out. It kind of has the same ending effect. Well, just like equations, let's add 6. Let's divide by 2, and we get x cannot equal 3. And now I want to write that as an interval. So just for one quick example, I'm going to show you how this would work on a number line. I'm not going to do it on every single one. Normally when we're in person, I like using people to kind of come up to the front of the room. But let me draw this one out for you guys. Okay, so we have our function f of x equals 1 over 2x minus 6, and we say the domain is x cannot equal 3. However, we write domain as intervals, right? We've been talking about intervals for the last couple chapters. So how do we write that? Well, on a number line, right, these are all going to be x's. This is negative infinity to infinity. And we're saying we can be everything except 3. We don't want to be 3. Absolutely not 3. If you plug in 3, 2 times 3 is 6. 6 minus 6 is 0. So 3 is our only problem child, so to speak. However, just because 3 is a problem doesn't mean everything else is. We can be everything to the left of 3. We can also be everything to the right of 3. So here's how we write that. Everything to the left of 3 would be negative infinity up to 3, right? This says all the x values to the left of 3, with 3 not included because we're using parentheses. Okay? Well, we can also be everything to the right of 3, right? This was everything to the left of 3. This is everything to the right of 3, and that would be 3 to infinity. Again, 3 not included. So this right here would be the domain written in interval form. A good way of looking at this just says everything except 3. And that's all that's all it is, right? It excludes everything. Sorry, includes everything except 3, which is not included on either side of 3. So that's how domain's going to work. I'm going to come back and do like one example when we get to other cases, but in general, this is the thinking here. Okay, let's go back to the presentation. Okay, and we're back. And just to go over that again, we're saying everything to the left of 3, everything to the right of 3. All righty, 1 over 1 minus x squared. Well, we want to make sure that the denominator does not equal 0, right? That's our red flag here. Okay, 1 minus x squared cannot equal 0. Well, we can factor 1 minus x squared. We can set each factor equal to 0. So we can be everything except negative 1 and 1. Okay, well, think about this. We can be everything except negative 1 and 1. We can be everything to the left of negative 1. We can be everything in between negative 1 and 1. And we can be everything to the right of 1. So I'm not doing this one on the whiteboard, but I think you guys see, oh, we excluded negative 1. and we excluded positive 1. Everything to the left of 1, everything between -1 and 1, and everything to the right of 1. So, be very careful and kind of think about this. Look for this pattern that when we had one x value that was a problem, we had 2 separated intervals. When we had 2 problem values, we had 3 separated intervals. So if you had 3 problem x values, what would the last one be? All right, how many intervals would that be? Alrighty, let's talk about square roots. Well, for square roots, we want to make sure that the inside is always 0 or bigger than 0. Case in point, we can be everything except negative numbers. Okay, so x plus 1 greater than or equal to 0. This ensures that everything we get on the inside is greater than or equal to 0. Well, subtract 1 on both sides, and wow, haven't we been writing intervals like this since like chapter P? This says everything to the right of 1 with -1 included. That's it. So stuff we were doing in chapter P, it's coming back. And that's sort of how this works for domain for square roots. Now, doing a whole bunch of examples, here we go. Find the domain of the 7th root of 400x squared minus 600x plus 800. Okay. But the rule we have for roots is for even roots. For even roots, for square roots, for 4th roots, for 6th roots. And 7th root is definitely not an 8th root. Sorry, 7th root is definitely not an even root. Think about when we were trying to evaluate odd roots versus even roots. We knew we can have negatives inside odd roots. You can take the 3rd root of -27, but you can't take the square root of -27. So because this is an odd root, the domain is all real numbers. Simple as that. Actually kind of nice. But now let's find the domain of the 6th root of x minus 12. Well, this is an even root, so we need to make sure everything on the inside is greater than or equal to 0. All right, x minus 12 greater than or equal to 0. Add 12. This says everything bigger than 12, so 12 to infinity. All righty, let's keep going. X minus 5 over square root of 3x minus 12. And here we have a square root, but it's in the denominator. So this was kind of like our 3rd red flag case. It's a combination of both those first 2 red flag cases with rationals and square roots. Normally, we're okay with our square root being 0 or positive. However, the second that square root or that even root is in the denominator, we're not allowed to let it be equal to 0 anymore. So instead of saying it can be 0 or bigger than 0, all we say is has to be bigger than 0, just greater than. Okay, well, we add 12, we divide by 3, all the x values bigger than 4, 4 to infinity, right? And specifically, we exclude 4 because if we had 4, 3 times 4 is 12, 12 minus 12 is 0, square root of 0 is 0. Oh, 0 in the denominator. So the only thing separating square roots in general versus square roots in the denominator is just whether or not we use a greater than or equal to sign. Okay. 15x squared plus 1 over square root of 2 minus x. Same thing. There's just a square in the denominator. We just want to make sure the inside is greater than 0. We don't want it to be equal to 0. It has to be strictly greater than 0. Alrighty, well, we can add x to... Okay, well, we can subtract 2 on both sides. We can divide both sides by -1, but think back to 1.6. When we divide both sides by -1, we flip the sign. Don't forget that. It's been a while, I understand, but divide both sides by -1, the sign flips to less than. This says all the x values less than 2, so everything to the left of 2. It's kind of weird to say that we can be, negative values for this, but think about what our square root is looking at, right? If x was -10, well, 2 minus -10 is 2 plus 10, and 2 plus 10 is 12. That's good for the denominator. But if you plugged in something like 3, 2 minus 3 is -1. Square root of -1 is complex. It's not a real number, so that wouldn't work. All right, one more case. In the event that you have a square root in the numerator and a denominator that separately causes a problem, what we're going to do is find the domains of each part separately and intersect them. So domain of the square root in the numerator, 0 is totally fine. So we have to make sure it's greater than or equal to 0. Subtract 2 and -2 to infinity. All right, we've done that before. But of the denominator, we want to make sure that the denominator does not equal 0. So x cannot equal 1. And that would be everything to the left of 1 with everything to the right of 1. And now what we're going to do is just intersect them. What does this interval and this interval have in common? Everything from -2 to 1 with 1 to infinity. So it has to be within these ranges. I know this extends all the way to -infinity, but let's plug in, say, -5. Well, -5 is okay for the denominator. -5 minus 1 is -6. That's good. But -5 plus 2 is -3. And we can't take square root of -3. So for square roots and denominators separately, take the domain of each part and intersect them. But this doesn't happen a ton. It does happen, but not a ton. Find the domain of 1 over 1 plus x squared. Oh, it's a fraction. Denominator cannot equal 0. 1 plus x squared can't equal 0. Let's subtract 1 on both sides. And you might think that you take the square root of both sides, square root of -1. Oh, that's not a real number. So there's no problem values. Every x squared is going to be not equal to -1. You can't square any number and have it be negative. So this is always true. Another way of thinking about this, there's always 3 types of numbers. There's negative numbers, positive numbers, and 0. Well, if we take a positive number and square it, it's positive. And then you add 1, and it's still positive. Well, we're looking for 0. Positive numbers are never 0. So this is good. Negative numbers, kind of similar, but you take a negative number and you square it, then it's positive. And then you just add 1 and you are still positive. So positive numbers aren't the problem. Negative numbers aren't the problem in this case. So it must be 0, right? Well, 0 squared is 0. 1 plus 0 is 1. And 1 doesn't equal 0 either. So all 3 types of numbers, positive, negative, and 0, don't actually cause any issues. Now, that's not a perfect way of thinking. It doesn't work nicely for all the other questions. But, if you get to a point where you're kind of like, what the heck is going on? There's pretty good rationalization for that. No pun intended with the rational. Okay, well, domain is the set of all x values that are included. So likewise, the range is the set of all y values that are included, or all the values that we can get by evaluating the function. Now, graphically, this is the set of all y values that appear in our graph. But it's kind of weird to solve for when it comes algebraically. Like graphically makes a lot of sense, no problems at all. But algebraically, it's very hard to determine range. Range is the set of all values that we get by evaluating the function. So are you going to evaluate the function at every x value in the domain just to see what y's you get? Absolutely not. So determining range algebraically, we're going to put on the back burner a little bit. We'll come back to that in 2.8 or 2.9. So some graphs. We've been doing a ton of graphing. And guess what? Graphing functions, no different than how we did it before. Plug in x and get a y or f of x value. So throw it back to 2.2 when we did like y equals x squared minus 3. You plug in x's, you get y's, table of values. It's no different, except now we're just using f of x's. So, but one thing that is interesting is that we can test to see if a graph represents a function. Well, that's called the vertical line test. Vertical line test says if your pencil or if your vertical finger, whatever it is, if it covers any 2 points at once on the graph of your equation, then the graph does not represent a function. Let's think back to that very first definition we came up with for functions. We said functions must use every x, but every x can only be used once. So if you have a vertical line and it covers a point here and a point here, it says that that same x value is going to two separate y values, and that violates the second rule of functions. So vertical line test says if your finger covers 2 points at once vertically, right? Your vertical finger covers 2 points at once, it is not a function. Okay, finger, pencil, whatever works for you, right? And we can get some information about a function by looking at its graph. For example, if AB is a coordinate point on the graph, then A is in the domain, B is in the range, and B is the value at A. But these are things that we already knew. Domain would be the set of all x values that you see, all the x values that are included. And like I said, range, not so bad to find graphically. It's the set of all y values that are included. So let's take this graph right here, and we want to find domain, range, and determine whether or not it's a function. Well, domain, set of all x values that are included. And how we read domain is left to right. Look at some of those domain examples. It was always furthest left we could go to furthest right we can go. So to find domain, we're going to follow this graph left to right and see what x values and y values are included. Y's will be, vertical. But let's all see all the x values we get. Well, this arrow tells us that we go forever down and forever to the left. So even though we don't see it on this specific picture, it does say by this arrow that it's defined for every value to the left of where this is pointing, right? Arrow says forever down, forever left. So we know this is defined for everything from negative infinity. So we're at negative infinity, we follow the graph, and we just want to see how far right we can go. Well, we can go up and down and left and right, and this goes forever up and forever to the right. So our domain is negative infinity to infinity. Even though we don't actually see every single value on here, this says that it is extending forever to the left and forever to the right. Range, similar, except when we read domain, we read left to right because x's run left to right, negative to positive. But y doesn't work the exact same way. Y running negative to positive is going down to up. Ooh, that's kind of weird. So range, instead of reading left to right or up and down, what we're going to do is read down to up. How far down can we go to how far up can we go? All right, how far down does this graph go? Oh, well, it's a little clearer that this goes all the way down to negative infinity. But how far up does it go? It goes up, and it comes back down, and it goes back up, and it goes up forever. So that's also negative infinity to infinity. Last but not least, is this a function? Vertical line test says, if our finger covers any 2 points at once, it is not a function. So I know that this, my little cursor here is not a nice long vertical line, but you should do it, follow along with your pencil, and see that at no point does your pencil cover more than 1 point at a time. Since it never covers more than 1 point at a time, it is a function. It's a problem when you do cover 2 points at once. Okay, similarly, let's do this for a circle. We already have an answer to the function part, but let's still take some information. Domain, set of all x values that are defined. So we're going to go left to right, see how far left and right we can go. Well, we see that the first x value that is defined, that has a value, is -3. Now let's follow the graph left to right. Everything between -3 and 3 are defined. Notice -4 isn't defined. There's no value here. 4 isn't defined either. The only values for which this graph has value, only x values for which this graph is defined is from -3 to 3. -3 and 3 included. Similarly, for range for the y values, the furthest down we can go is -3. Furthest up we can go is +3. So that's not so bad. However, bigger question, is this a function? And the answer is no. Take your pencil, cover this line right here. Do you notice that your pencil covers this point right here and this point right here? Oh, well, your pencil covers 2 points at once. That's the definition of not a function. It fails the vertical line test. We could say this one passes the vertical line test. This would be fails the vertical line test. Okay, so with that said, that's the end of 2.4. 2.4 really sets the stage for functions, but 2.5, we're going to get back to looking at some of the properties of functions. So I will see you in 2.5. Bye.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leswowska Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.